let's get started. Today we're very happy to have Zhaofeng. Zhaofeng is actually a PhD student in my group. He's a 30th PhD student. And today he'll be telling us about the semantic hub hypothesis. So let's welcome Zhaofeng.
Okay, thanks, Jim, for the introduction, and thanks everyone for coming. And yeah, today I'll be talking about our recent work to appear at ICLA this year, the semantic hub hypothesis, language models share semantic representations across languages and modalities. And before we start,
oh, thank you. I've been waiting for this. And how this going to change the mechanical fun. Don't feel don't clean efficient.
that's like our language models are supposed to be.
All time coming in.
Okay. So we saw that Meccano can do a lot of different things. And just like our language models, our language models can process a very diverse kind of data. They can process inputs in different languages. They can process non-linguistic inputs like arithmetic expressions or codes, or even input in other modalities like images and audio. But how do our language models process such diverse input data using only one single set of parameters? One possibility is that it uses disjoint representation spaces to process different kinds of data. For example, it uses a subset of its parameters to process English data, another for Chinese data, etc. But obviously, this is not efficient because for different languages, there are a lot of knowledge that is transferable. And we can take inspiration from the cognitive science literature. So cognitive scientists theorize that in our human brain, there is this modality invariant hub that centrally processes information from a variety of different modality-specific processing units. And these modality-specific spokes interact with the real world and send information to this central semantic hub. And cognitive scientists have also found similar mechanisms for processing different languages as well. So we hypothesized that language models on a very, very high level implement something similar. So to illustrate our hypothesis, let's consider the multilingual setup as an example. So the first part of our hypothesis is that parallel sentences, so sentences that have the same meaning but in different languages, should have similar language model representations. For example, the display here is not good, but imagine there's some language model representation here. The color is kind of faded. So if we consider intermediate language model representations of two a pair of parallel sentences, so this paper is so hard to. By the way, you can probably imagine my trauma when I wrote this example. And its Chinese equivalent, we should expect high similarity in the language model intermediate representations. So we can test this pretty easily. We just take professionally translated parallel sentences between English and Chinese, compute and pass these parallel sentences through a language model, take their intermediate hidden states and compare the similarity between the English hidden representation and the Chinese hidden representation at each layer. And cosine similarity, by the way, ranges from 1 to -1. So in general, we see pretty high cosine similarity between parallel sentences across a variety of different models. In particular, we observe this trend that the cosine similarity is really higher in intermediate layers and lower on the two ends. And this is pretty intuitive because the earlier layers still need to process language specific inputs and convert that input into this language agnostic representation space, and the final layers needs to convert back to the original language. So the earlier layers and the later layers are kind of like the modality specific spokes that we saw a bit earlier. And so the cosine similarity would be a bit smaller. Oops. Okay. But the raw cosine similarity here is not very easy to interpret. Like, what does a 0.5 cosine similarity mean? So we can consider a baseline, which is the cosine similarity between non-parallel sentences. Again, the figures here are, the display is not great, but you can imagine that we expect the cosine similarity to be higher between the hidden representation between parallel sentences versus the hidden representation between a Chinese sentence versus some other random English sentence. So this is the same plot that we saw earlier. And instead of just plotting the raw cosine similarity, we can subtract the cosine similarity with this baseline number using a random non-parallel sentence. But overall, we see very similar trends. So this is the first part of hypothesis, that there is a shared representation space between different languages. And the second part of hypothesis is that this shared representation space is scaffolded by tokens in the language model's dominant language, which is usually English, but not always. What do I mean by that? So given some prefix in some input language, whatever the input language is, we hypothesize that the representation of that prefix should be close to continuations in the dominant language, again, usually English. For example, the representation of this same Chinese prefix should be similar to the embedding of the English word right, which would follow this prefix. This is in some sense just a corollary of our first hypothesis, which again dictates that the representation between the Chinese prefix and the English prefix should be similar. And the second approximate equal to just comes from the autoregressive language modeling objective that the representation of prefix should be similar to the representation of the continuation. But we actually claim something stronger. We say that similarity between the Chinese prefix and the English continuation should actually be larger than the Chinese prefix and Chinese continuation, because the model is actually using its dominant language to scaffold its reasoning process. It's kind of similar to our human brain as well. And this would allow us to easily interpret model behavior when it processes diverse inputs and to better control the model, as we will see in a bit. Yeah, again, so given Chinese prefix, we expect high similarity with English continuation than a Chinese continuation. I want to make a short digression and talk about the logit lens, which is a technique commonly used in interpretability studies. So some notation first. So that denotes the transformer hidden state at some layer and position using this notation HLT. And when we need to generate the next token, we take the final layer hidden states denoted by big L, do a multiplication with the output embeddings, and do a softmax, and that's the output distribution of the next token. The typo. It's a very similar process. Instead of doing this at only the final layer to compute the next token distribution, it performs this at intermediate layers as well. And often people find it to yield very interpretable output distributions, and we'll see this in a bit. But this is possible because of the residual streaming transformers. So in a transformer, the hidden states are built up via a series of small additive updates, and it is unlikely that these small additive updates very drastically shift the basis of the representation. So the same output embedding should still roughly correspond to the structure of intermediate hidden states. And a special case of this is that if we don't take the softmax and just do the argmax, so look at which token is the closest to the current hidden states. So basically, we look at all the tokens in the vocabulary, look at their output embeddings, and see which one is the closest to the hidden states as measured by dot product. So as an example, this is taken from the original blog post that developed this method. Here they feed a sentence into a language model. Specifically, we train GPT-3 and blah 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 blah. And at each position and at each token, they take that hidden state. They look at which token in its vocabulary is closest to the hidden state. And this is really very interpretable. So to zoom in a little bit, given this prefix specifically we, let's look at some intermediate tokens. So the ground-truth token is like specifically we train, but the intermediates, the closest intermediate tokens are things like specifically we hope, we target, we focus, we found, we simulated, we demonstrated. So these are all very natural tokens that can follow this prefix. So we can do a very similar thing with our language models. So we feed our language models a Chinese prefix and look at each layer the closest token to that particular hidden state. And we found that it's pretty much always in English, especially in the later layers. And it semantically corresponds to the Chinese prefix as well here. So here it says enter the entertainment and industry is a natural continuation in English. But in the final layer, of course, it needs to generate the Chinese. And I should say that we are not the first group to discover this. There was this previous paper that found a similar behavior, although they only focused on very, very simple and synthetic tasks. So this kind of lexical pattern matching tasks. And we generalized their findings and showed that this happens just in general for just general domain language modeling. And also this happens for many different kinds of models, and as well see different data types as well. Okay, so this is pretty cool, but how do we quantify this? Going back to our second hypothesis, which said that the Chinese prefix should be similar to an English continuation than Chinese continuation, let's just write these using these notations. So H is the hidden representation of this prefix, O is the output embedding of some English token or Chinese token. If we operationalize similarity using dot product, this is what we have. And that happens if and only if the logit length probability is larger for the English word than the Chinese word. So we can just take some Chinese prefix, compute the probability at some intermediate layer using the logit length of an English token and a Chinese token, see which one is larger. And this is exactly what we do. Again, we take professionally translated parallel sentences, feed Chinese prefixes into Llama 3 and compare the continuation token in 2 languages. And we would expect in middle layers, the English token should be more like the Chinese token because that's what scaffolds the model's reasoning process. And since that's the dominant language of the language model. But in the final layers, because the model eventually needs to output Chinese, we expect the Chinese probability to be higher. And this is exactly what we observe. We can also look at more global language trends. So on the top left, we feed Llama 2 either English input or Chinese input. When we feed the English input, the most likely language is always English, denoted by this pink color. When we feed the Chinese input, again, in the early to middle layers, English is the more likely language, but in the final layers, Chinese become more likely. And similar trend holds for Llama 3, although the change is a little bit more abrupt at the end. And also for 70 billion models, the trends are highly similar to the 7B models. And also this trend very nicely flips for a Chinese dominant language model. So at the bottom left, so bytraining 2 is a Chinese dominant language model. And when we feed it Chinese inputs, of course, Chinese is always the most likely language. But when we feed it English inputs, Chinese dominates in the early middle layers, but English is more likely towards the end. And for a multilingual model like Bloom at the bottom right, we don't really identify a dominant language in the middle layers. So this kind of light green color is neither English nor Chinese. And when we manually inspect these, the closest tokens, usually they are semantically vacuous tokens like white space or punctuation marks. So which means that these multilingual models do not really use any dominant language to structure their internal reasoning process. Not to say that they don't have a shared representation space, they do, but they just don't have a dominant language to scaffold this. And people have found similar effects where models think in their dominant language. So here, for example, so this is, I think, the CTO of Hugging Face, found that the Kun model, which is a Chinese dominant language model, reasons in Chinese, even though the input is in English. And people have found this for DeepSeek as well. And also sometimes O1 from OpenAI, which is certainly not Chinese dominant, but perhaps there are some narrow problems domains where it has seen more Chinese data than English data. So this is a bit different from our setup. So we focus more on the intermediate hidden states, but not on the explicit reasoning process. But I think the high-level motivation is very similar, and I think it will be really interesting to extend our study to analyze this particular code switching behavior. Okay, so this is the multilingual setup. We can also look at other data types like arithmetic expressions. So given an arithmetic expression like 75 equals to 70 plus, now of course we would expect the Arabic numeral 5. But in the intermediate layers, sometimes we find that the English word 5 is the closest token to the hidden states. Again, it's likely because English is the dominant language of the language models, and they use English to structure their reasoning process. And we can do this same experiments that we did for multilingual experiment. So for our first hypothesis, we look at the representation similarity between an arithmetic expression and the same expression but verbalized in English. So we break down our data by 3 categories. So those that are exact translations, those that are not exact translations, but nevertheless have the same value, and others. Let's just look at the solid lines for now, which is Llama 3, the dotted lines for Llama 2, but the trends are pretty much the same. exact translations have the highest similarity. Those that are not exact translations but nevertheless have the same value still has slightly higher similarity than those that have different value. And when we subtract the baseline as we did for the multilingual experiments, again we see a similar trend, and also the similarity is higher in the middle layers than the two ends, although this is more salient for lemma 2 than lemma 3. So this is the first hypothesis on the repetition similarity. We can also test the English scaffolding of these language models. So this is very similar to the example that I showed like 2 slides back. We feed these prefixes into the language model and look at if the models are thinking about the Arabic numeral 2 or the English word 2. We can actually visualize this. So we do a PCA and reduce the language model hidden space into 2 dimensions. And we find that the English words occupy one cluster in this representation space, and the Arabic numerals occupy another cluster. And the hidden states evolve as indicated by the color getting lighter from neither of those clusters, progress through the English cluster, and eventually shoots off to the Arabic numeral cluster. This is a bit hard to read on this display, but yeah. Yeah, I can also do similar study as earlier, and we find that the English words have high closure length probability in early middle layers, but the Arabic numeral would eventually dominate towards the end. Let's look at another data type, code. So given this prefix, so like for I in range 0, 10, the next argument is the step argument. And because the function asks us to print even numbers, the natural continuation here is 2, and indeed language model eventually outputs 2. But it thinks about what argument it is internally and thinks the word step. Even though this is like step is not a contextually defined variable, so it would not be syntactically valid to output this word. But the model is actually thinking about the argument name before filling it out. I'll skip this example. For this third example, so this is about type annotation. After this function declaration, after the closing parenthesis, what should follow is the return type annotation, which has the syntax like arrow, bool, comma. And indeed, the model eventually outputs this arrow. But in the intermediate layers, it thinks returns, which again would not be valid Python. But semantically, it makes sense. And one more example. So for this list literal, so 1, 2, 3, eventually the model would output 3. But in the intermediate layers, it thinks and this is kind of natural for us. We would say things like 1, 2, and 3. And so this is reflecting trends in natural language as well. I'll skip this for the sake of time. But for the function arguments example, we can scale it up. So we take some programming data sets. We extract all such functions. We look at whether the semantic row or the argument name has a higher probability, or if the surface form has higher probability. And we find that in early middle layers, the hidden states are closer to the argument name. But in the final layers, because it eventually needs to output the surface form, it converges to that. And this is a very similar trend that we've seen before. For the sake of time, I'll skip some of these data types, but in general, we find similar trends for other data types as well. For example, we find that language models assign similar representations between English words and these categories prescribed by linguists. I'll skip the experiment details time. And we also identify similar patterns for multimodal models. So, for example, given a vision language model, if you give it some patches for sky, it would actually think about the word sky. So the closest token to that hidden state is the English word sky. And also like background, I think also makes perfect sense. Yeah, we have experiments that validates this. And similarly for audio as well. So if you give it a snippet of piano sound, it would think about the word piano. But yeah, if you're interested, you're welcome to check out our paper for the experimental details. So a brief summary so far. So we identified that for a variety of different input data types, semantically equivalent input pairs would receive similar representations from the language model. And this shared representation space across different languages and across different modalities is anchored by tokens in the model's dominant pretraining language, which is, again, usually English, but it could be others. And inspired by the cognitive science studies, we call this space the semantic hub of the language models. There's another question that we want to investigate. Is this semantic hub merely vestigial? So what do I mean by vestigial? So one common example to illustrate this is the human appendix. So a lot of people think that appendix just comes with evolution. It's just there in our bodies, but it's not actually useful for anything. So it is possible that the semantic hub also just forms through large-scale autoregressive pretraining, but does not actually functionally affect the behavior of language models. But we actually showed that the language models actively use this mechanism to calculate its outputs. So to illustrate this, let's consider a very simplistic setting where we just have two dimensions. One dimension is causal dimension, the important dimension, and the other one is the not important vestigial dimension. So suppose this is the representation strategy from the language model, where we have two words and two images. This is a good representation strategy because although they are a bit further apart on the vestigial axis, that's not so important, they're perfectly aligned on the causal dimension. And when we calculate the similarity, it would be pretty high. But an alternative bad representation strategy is this, where they are reversed. However, because they are closer on the vestigial axis, the causal similarity would still be pretty high. So just from a static analysis, like we have been seeing, that's not enough to distinguish between these two possibilities. So how do we tell them apart? Usually in the interpretability literature, people use causal intervention techniques to differentiate between these two possibilities. So specifically, given an image of a dog, well, if we ask a vision language model, what is this animal? Of course, we would expect the word dog. But instead, let's consider this delta vector that goes from the word dog to the word duck. And if we apply this delta vector on the hidden representation of the dog, that would mislead the model to think it's a duck because we manipulated the hidden representation. And now we would expect the model to say duck. But on the right-hand side, this is not so well defined because the representation of dog would just go to some weird random place. And so this is how we would intervene on the model representation. So we can pretty much do this exact recipe. We give the model an image of dog or audio of a dog barking. We add the embedding difference between duck and dog to the representation of either the image or the audio, and ask what is this animal, and we would expect the word duck. Although there's a small confounder here, because we're adding the embedding of the word duck, that might just simply lexically bias the model towards generating the word duck without actually any deep reasoning behind it. So we still do a similar thing, but the questions that we ask would require deeper reasoning. We ask things like, is this animal a mammal? So there will be less lexical level or surface form confounding. So for the audio setup in particular, we take an animal sound, we compute this delta vector or steering vector B by if this animal is a mammal, we take some random non-mammal name, subtract it by this mammal's name, and vice versa. We scale it by a constant and add it to some intermediate layer. And we ask the model, is this animal a mammal? And look at the probability of the model thinking, yes, it is a mammal. And the intervention is generally pretty successful. As we increase the intervention strength, we increasingly lead the model into believing mammals are non-mammals and non-mammals are mammals. And we can do a similar thing for other data types, for example, for code. So for the range function, ignoring the step arguments, there are two versions, range end and range start end. So if we have this prefix print to 10 for I in range, open parenthesis, we would really just say 10 and then close parenthesis. And in other words, use the single argument version. But we can steer the model's behavior. Again, remember that the models tend to, in its intermediate layers, think about the function arguments before filling it out. If we add this delta vector, we actually find that the model would tend to use the two argument version, even though the 0 is redundant, is useless. But because it's thinking, oh, I need to now fill the argument start, I need to use this two argument version. And again, as we increase the intervention strength, the orange line is correct. It's blocked by we steer more and more inputs to use the two argument version. And for the sake of time, I'll just talk about these intervention on these two data types, but we do interventions on the other data types and back as well. And you can check out our paper for those experiments. And our work is related to a long line of work that investigates the alignment of separately trained representations. So, for example, for the multilingual setting, people have found that if you separately train two monolingual models, so for example, one model of English and one model of, I think this is Italian, people found that these two models would have the representation space have similar structures such that the two spaces can be aligned via a transformation. Similarly, for multimodal, the multimodal setup, we have found that if you take an image model and a text model, again, they would have similar structures that they can be aligned by training a linear projection layer. But our work differs from this line of work because we show that for one single model that can process different data types, different languages or different modalities, the representation of the different data types are already aligned. We don't need to train another transformation layer. This is also related to the Platonic representation hypothesis from Philip's group here. which shares a high-level motivation, and they argued philosophically that this is possible because the different modalities are modeling the same underlying reality. But their specific operationalization is still more similar to what we saw in the previous slide. They train separate single data type models and argue that have similar structures that can be applied. So obviously, this representation strategy has a lot of benefits. It is a very efficient use of the model capacity because there's a lot of knowledge that is just transferable across languages or across modalities. And this enables good generalization between languages and modalities. So for example, I won't focus on this, but in previous work, we showed that you can use, so in an alignment setup, you can use an English reward model to align a Spanish language model and achieve sometimes even better aligned model than using a Spanish reward model. And this is possible because the English reward model captures language universal signals that can be used to condition the Spanish language model. And this is likely due to the mechanism that we investigated in this work. And I think as future work, it will be very interesting to think about, is it possible to more explicitly encourage this? So we found that this already autonomously emerged to some extent just through autoregressive pretraining, but can we more explicitly encourage this representation strategy? But I think there are also concerns with this. So the reliance on the model's dominant language might bias the reasoning process towards the dominant language. And this might not always be ideal. There might be words that are not translatable across languages. There might be text that where we do want different answers depending on the language or the culture where this is asked. So some amount of language specific processing would be helpful here. And also, as we saw, the numerical reasoning processes of these language models are correlated with natural language. This might not always be ideal. As we know, different languages have different number representation systems, and this is real. They even have different number base. Some language use, well, interesting number base, like base 23 or base 27. And so I think ideally we want to delegate to language-specific or modality-specific processing whenever appropriate, while still maximizing the amount of shared processing. And I think this would be very valuable future work to investigate. And yeah, that's it. Questions?
I have a very nice talk. I have a question on the multimodality part. So for VOMs or for audio OMs, they usually have this pretraining that produce semantic representation for the LMs. And I wonder how, if your hypotheses account for the, because if the semantic encoder isn't trained properly, or if it's trained from scratch, like the results will be much worse. So it seems like at least for multimodality, it depends heavily on the encoder. And then secondly is for I guess for VLMs and OMs, the task that you look at is English. So it's natural that when you look at the logits, they are English. Let's say if you look at like image generation, audio generation for your task, and then you look at the intermediate states, they are English, and I guess that's more aligned with your hypothesis.
So first question first, when you say like semantic encoder, right?
Yeah, so like for VLMs, people typically train, they have this like clip or single encoder.
Yeah.
For the LM to be conditional. And then for audio, I guess you're also using pretrained audio encoder to condition the LM as well.
Actually, not in our sense. So for VLM, we looked at Lava and Chameleon, which do not use, I think, a clip like pretrained vision encoder. For Chameleon specifically, I think it's just jointly trained on visual language text from scratch. So in some sense, that's similar to training on multiple languages at the same time from scratch. That's the same similar things.
I will observe maybe like in reason this intermediate step, or maybe intermediate doesn't show, but maybe in reasoning, using one particular language versus another might significantly reduce the reasoning token that's needed.
Yeah, as I said, this is slightly different from our research question where we look at only the vertical processing, like states rather than the horizontal, like chain of thought style reasoning. But I think this is very likely. I think if you look at the corpora between different languages, usually it's likely that they might have different distributions on different counts. So maybe some tasks are just better to be processed in certain languages and, like, for example, use shorter reasoning chains, something like that. But I think that'll be very interesting research question. John, maybe you can just end here.